Perfect. Thanks very much. I'm very in a good situation because I had already so many introductory talks that I can all use in my talk, so I can skip over most of the preliminaries in my talk. That is nice. Yesterday, and I wasn't even sure anymore, but the last days we thought that we had a kind of similar program, and we actually checked. It was actually exactly 10 years ago that we had a very similar themed program here at the ESI. And it's very nice that many people that I met back then are here right now. And as I also remember how much pain it was to organize this program and how tiring it was to organize this program, I mean, it was very beautiful and I enjoyed it until now, but I would really invite everyone here to thank all of organizers and in particular to give a big round of applause to Barbara right now, just for all of her hard work here. And for continuing to build our communities. Thanks a lot. I want to start this talk by acknowledging some of the many co-authors on whose work this talk is based. So it's I plan to have a more theoretical part in the first half of the talk, or maybe first 3/4 of the talk. But at the end of the talk, I want to show you some numerical examples. The theory is mostly based on the people on the top row. So Martins and Philip, who were both kind of my PhD siblings, and Peter. But also the more recent work is based on Simoa, whose student is currently here, Ronnie. And the more applied parts are based on work with Nicola, Emanuel, Eric, and Yashil. And all the pictures that you will see in the second part are, of course, from Emanuel, so blame him. This is not very... Okay, so I want to start a tiny bit with giving some motivational remarks why we want to study Riemannian geometry in infinite dimensions, and also about the history of infinite dimensional Riemannian geometry. So I learned this quote from Peter, as I learned many things in my life from Peter, and it's kind of interesting that the idea of infinite dimensional manifolds is not at all a new idea, but can be really traced back to the very birthplace of Riemannian geometry, namely to the Habilitationsschrift, I should be able to pronounce this, habilitation thesis of Riemann, where he already mentioned that a manifold is not necessarily a finite dimensional concept, but that there are many, or that one can envision situations where one really needs an infinite dimensional amount of information to describe an object, and so a manifold can be an infinite dimensional object. And actually, he already back then mentioned the topic that we will discuss today, which is kind of shape analysis, because he described to describe the shape or the shape of a region or of a shape of a solid figure. So it's really not at all a new idea. Indeed, if we think back about our first differential geometry class, we all learned that a manifold is something that looks like a Euclidean space. How can we define this to infinite dimensions? Of course, we cannot anymore say that it's kind of like a Euclidean space, but we just assume that it looks, or in infinite dimensions, we just need a replacement, some infinite dimensional vector space, and depending on what it is, it might be a Hilbert manifold or a Fréchet manifold, if you want to even be more general. And in our context, a lot of the things that I will do today will be, unfortunately, Fréchet manifolds where even less of the finite dimensional theory works out. Okay, so I said it's kind of pretty simple to define an infinite dimensional Riemannian manifold. However, it turns out that many of the things that we are used from finite dimensional geometry do not work anymore in this infinite dimensional situation. And the first thing, and kind of maybe the most important distinction here, is that in infinite dimensions there exist two different types of metrics. They can be either strong Riemannian metrics, which mirror in many ways the finite dimensional situation, or weak Riemannian metrics. So what is a strong Riemannian metric? So in finite dimensions, we know the tangent pendle is isomorphic to the cotangent pendle, and the Riemannian metric is a bijection between the tangent pendle and the cotangent pendle. In infinite dimensions, this is not never the case, but often not the case anymore, and the cotangent bundle is often much bigger than the tangent bundle. And so we cannot hope in many situations that the metric is an isomorphism or a bijection, but we can only hope that it is injective. And in a situation where our Riemannian metric is only injective, we call it a weak Riemannian metric, but if it is still a bijection, we call it a strong Riemannian metric. Indeed, it's kind of important to know there is some classical textbooks that treat the infinite dimensional case, and they don't distinguish between weak and strong Riemannian metric, but they only mean strong Riemannian metrics. The textbooks like Lang are really only written for strong Riemannian metrics. Until very recently, there was no comprehensive textbooks on weak Riemannian metrics. I think there have been two nice books that I can recommend for this. One of them is lecture notes actually from C, which is 3 years ago or 4 years ago, and a bit later, Alexander Schmeding, who some of you might know, wrote a textbook on weak Riemannian geometry, which I think is very nice. Okay, so what are the problems and what are some... Not the fuse, my laptop. Sorry. Then I just plug my laptop back. Yes. It will not turn off if I plug it. Sorry for that. Did I destroy it? Okay. Okay. So what are some of the problems in infinite dimensions? The first thing is, and I will try to show you some example, some specific example for all of these wronggoings. So the first one is that the geodesic distance might be degenerate. What do I mean with this? Usually we will see it in more detail, but it means that some Riemannian metrics in infinite dimensions cannot be used to compare anything, because it will say that they are all the same. This is really a phenomenon that only happens for weak Riemannian metrics, but not for strong Riemannian metrics. Furthermore, the geodesic equation and the Christoffel symbols might not even exist, and we have seen some of these examples implicitly in Klaas's talk, but I don't think he emphasized it, and I will try to show you something about this. And furthermore, and this is a little bit connected to the geodesic distance, or we believe it might be connected to the geodesic distance, is that the curvature might be locally unbounded. What do I mean with locally unbounded? I mean that on a specific tangent space, I might have unbounded curvature. And also this is only for weak Riemannian metrics. And the last one, which is even true for strong Riemannian metrics, is that we have just no theorem of Hopf-Rinow, and I will spend a bit of time to show you some of the counterexample and also show you what we still have in infinite dimensions. So next, I just want I really don't need to talk much about this because we have this seen very nicely in Klaas's talk and also a bit in Barbara's talk, but I still want to talk a little bit about some motivations. Why do we want to study infinite dimensional Riemannian geometry? And we will see, and we have seen also already 2 different ones in this week, and I just want to recall them a little bit. The first one is the area of geometric hydrodynamics, which is based on the idea that we can model fluid dynamics on the diffeomorphism group or on the volume-preserving diffeomorphism groups if we want to study incompressible. And it was this very beautiful insight of Arnold in the 60s that Euler's equation for the motion of an incompressible fluid can be expressed as a geodesic equation of an infinite dimensional Riemannian manifold. Namely, I take the diffeomorphism group or the volume diffeomorphism group and I equip it with its natural L2 kinetic energy, which can be interpreted as a Riemannian metric. I calculate its geodesic equation, and if I write it down in Eulerian coordinates, I get exactly the incompressible Euler equation. After Arnold, a similar observation has been found for many other fluid equations. Just to mention some, the Kamasa-Holm, the KdV, Berger, more recently the SQG and the whole beta SQG family. So there's really a whole magnitude of different equations that can be interpreted in this setting. And even more, this interpretation has been really used also to find analytic results for the corresponding PDEs. I think notably there's a recent paper by Vladimir Sverak, for example, which I think is very, very interesting result, where he used Arnold's geometric interpretation for the incompressible Euler equation to prove new results on Navier-Stokes in the context of vortex rings for Navier-Stokes. Very enjoyable paper that really uses the geometry and achieves results that would not be able or were not be able to achieve without this geometric interpretation. So geometric data, as Alain already said in his talk, what is a shape? A lot of things are a shape. And it's kind of maybe too much to ask for to get one description or one theory for any kind of shape space. I think the first thing is, again, so why is a shape an infinite, or why is shape space an infinite dimensional space? A shape is an inherently very finite dimensional object because it's something that we can observe, some geometric figure. That is absolutely true, but the collection of all shapes of a certain type will be an infinite dimensional manifold or an infinite dimensional space. And depending on what types of shapes you want to study, you will need a lot of different theory. We have seen these beautiful multi-scale shape spaces that appeared in Alain's talk. The ones that I will observe, does this work? This here? Second? Yeah. So the types of object that I will do most in my talk will be curves and surfaces. So it will be the shape space of unparameterized surfaces. It will be my main example. Although I think the focus of my talk is rather this particular space, but just to emphasize, and it's kind of a nice, rich family of geometries where I can show you all of the things that can go wrong. So what do we want to do in shape analysis? And pass again everything of this back to Alain's talk, but in some way we want to compare, classify, and describe objects, and we want to have a statistical framework that really allows us to learn something from a population of shapes. And what are the difficulties? I mean, these types of, in general, most shape spaces are inherently nonlinear, so it's not per se defined what is the addition of two shapes, what is the average of two shapes. And in addition, they are at least high dimensional if we work in a discretization, or infinite dimensional in theory. So these two things together are kind of a difficulty that we have to overcome. And indeed, Riemannian geometry has shown over the past 20, 30 years maybe to be a good tool to tackle their difficulties in this context. I think one of the things is Riemannian geometry really models a very intuitive notion of similarity, because it does not define an ad hoc distance on the space, but it's based on deformations, as we all know. So we kind of consider two objects closely related to each other if they only differ by a small deformation. In addition, there is a whole area that deals with how we can define geometric statistics or statistics in a Riemannian framework. And if I'm correct, there will be a lecture course by Xavier Penec next week on this. So once you have defined a Riemannian framework, there is already a lot of things known how we can extend methods of linear statistics, of standard statistics, to this curved setting. Yeah, I think these are the main advantages, but for much of this, or for a more in-depth look on this, I refer to Xavier's talk next week, which hopefully many of you will have the chance to see. Okay, so now I want to start by really considering one specific manifold, or maybe three specific manifolds, but one type of manifolds, and I will equip them with different Riemannian metrics. I will discuss how we can kind of define some natural Riemannian metrics, and we will see some surprising degeneracies as we have discussed on the first slide here. Okay. So the main object in these talks are manifold of curves, surfaces, and diffeomorphisms. But to have kind of a unifying framework for all three of them, I just consider the space of emergence from some parameter space D into d-dimensional Euclidean space. So what should we think about the domain space D? Just think about it of either S1 or S2. S1 for curves, S2 for surfaces. And we don't want to have only smooth mappings, we want to have some additional assumption, namely we want them to be emergence. This is not really any restrictions on the type of shapes or shapes that we can represent with this, it's just a restriction on the parameterization of my object. Okay? Why do I say this kind of includes diffeomorphisms? It kind of includes diffeomorphisms if you take instead of RD as the target space, the domain space itself. Not completely formally correct, but for the purpose of this talk, that's fine. Okay, so how is this an infinite dimensional manifold? The space of emergence is an open subset of just smooth mappings. Smooth mappings are Fréchet space, are a vector space. What is the simplest example that you have ever seen of a finite dimensional manifold? The first example that you learn in your differential geometry class is it's an open subset of Rn. Here we have kind of the simplest example of an infinite dimensional manifold. It's an open subset of the Fréchet space of smooth functions. So if you have an open subset of a vector space, it's very easy to characterize the tangent space. It's just the surrounding vector space. In other words, a tangent vector is just a mapping from the domain, a smooth mapping from the domain into the tangent space of the target space, but we just have Euclidean space, so it's just a mapping into Euclidean space. And yeah, so we have found our don't like clickers. Okay. So sorry for that. What is a tangent vector? Let's talk again, continue talking a little bit about tangent vectors, because I think the last definition, although it's kind of clear, is somewhat abstract. So I'm like a very visual person, so I always like to look at an example. And here we see two examples, namely we see a curve on the left and the tangent vector to a curve. And it's kind of the most natural thing of what we could think would be a tangent vector to this curve. It's a deformation vector field that sits on the curve. So at each point of the curve, it gives me a deformation direction and the deformation strength. And very similar for the surface patch that we see on the right. Now we have as a tangent vector deformation vector field that sits on my surface and gives me a deformation direction and a deformation strength. Okay, what is the first thing? We want to do Riemannian geometry, so we want to discuss what is a Riemannian metric. A Riemannian metric takes two tangent vectors and a foot point and gives me a real number and has the conditions of an inner product. And so, in other words, given two smooth functions and an immersion, we want to use this to express it as a real number or to get a real number out of it. And once we have defined a Riemannian metric, we can define the induced geodesic distance. And the induced geodesic distance is we are looking for all paths that connect to given curves or to given surfaces. And we try to find the shortest path with respect to our Riemannian metric. Okay. I already introduced the diffeomorphism group, and it's also appeared a little bit in several other talks, in particular also in Barbara's tutorial about gauge invariance. And we will see the same thing here in a maybe slightly more complicated situation than this morning, or more specific, but at least more specific. So the notion of an immersion or of a curve to describe a shape is kind of the wrong notion yet, or most applications it will be the wrong notion. And I think there's two kind of examples again in the context of curves and surface to visualize this. So what do we see on the left? On the left we see two different immersions from the circle into the plane, where the color coding encodes the parametrization. If I consider them as immersed curves, these are completely different objects in the space of immersions. However, if I'm just interested to describe the shape here, I usually don't have a color coding, so I would like to have these two skulls to be the same object. We want to get rid of this. We want to get rid of this operation, namely we want to get rid of the reparametrization action of the diffeomorphism group. And this is very much what we had in today's tutorial, just applied to the space of emergence, where we want to quotient out the diffeomorphism group action. On the right, you see kind of the same example, but rather in the context of the data already. So we have two simplicial complexes representing a surface in R3. And the only difference between these two surfaces is that we have remeshed them, and we would like to identify this again. And we will discuss, at least for the first half of the talk, I will only discuss how to do this in a smooth setting. But then in the second half, or the second last part, I will show how Blanche's talk will help us to deal with this in reality and get rid of this action in the context of real data. Okay, so the image that I like to keep, the image that I like to keep in my head for this is kind of this nice quotient bundle construction. So on the top, we have the shape space, where on each fiber, we only change the parameterization of my object. But if we move from one fiber to the other fiber, we change the shape of my object. And if we want to go to shape space, the shape space is this quotient space on the bottom, where we have factored out the action of the reparametrization group. And what do we need to be able to do with a Riemannian metric on the top space to go to the quotient space? We will require our metric, as we have learned today, to be invariant with respect to the action that we want to factor out. If this is the case, then we can induce a metric on the quotient space such that the projection is a Riemannian submersion. What is a Riemannian submersion? Essentially, it is a very convenient construction that allows us to do a lot of the calculations on the top space instead of on the quotient space. I might have been a tiny bit hand wavy here again, because invariance is not necessarily enough in this infinite dimensional setting, but this is a subtlety that I will ignore for this talk. Okay, so we are back. We want to define a Riemannian metric, because I wanted to give you some Riemannian metrics from which we can see kind of nice phenomena. So what is the simplest way to introduce a metric? So we said tangent vector is just a function. So what can we do with a function? We can just integrate the function. So we could just take some measure dx, take our two functions, pointwise, they are just elements of Rd. We take the inner product, and then we integrate them up. Okay, why does this not work? Because it's not invariant. If you try to do, we all know how to do a coordinate change in integral, but if dx is a fixed measure, this will change the value of the integral. So if I reparameterize f, h, and k, both with a diffeomorphism, this will give me a different value. So that is not a good idea. Okay, so the next thing you can do is, instead of using dx, we use the induced surface measure of my foot point f. So instead of integrating with respect to some fixed dx, we integrate with respect to the volume form of my foot point f. So just to say, in the simplest case, if we are working with curves, what is vol f? It's just arc length integration. So it's just norm c prime d theta. Okay, this works out nicely. It is invariant, and it will induce us a metric both on the top space and on the quotient space. Why does this not work? This doesn't work. I mean, it works, but why is it not a good idea for shape analysis? It's kind of one of the maybe the most natural example of a Riemannian metric in infinite dimension that has zero geodesic distance. What do I mean with zero geodesic distance? I mean that given any two surfaces, there exists a path of arbitrary short length connecting them. So since the geodesic distance is defined as an infimum over all of these paths, I get zero distance. This was a really, in my opinion, very surprising discovery, because if you just look at the metric, that's not something that you would expect. Nicely well-defined inner product on each tangent space. This was first proven on the shape space directly and not on the space of emergence, but later it was also observed that it's also actually true for parametrized surfaces. So the geodesic distance manages both on the top space and on the quotient space. It also holds on the full diffeomorphism group, and it holds also on the Virasoro bot group. Peter always likes to say that the original proof of this was not found by him, but by David Mumford's computer. So I think how they realized is they actually wanted to use this metric for doing some shape analysis tasks for curves. And as they discretized the curves better and better, the paths got shorter and shorter and more and in some way worse and worse. And then they kind of tried and managed to prove this result by showing that what they saw on the computer was really the degeneracy of the metric. It is worth to note here that the very first example of a Riemannian metric with vanishing geodesic distance was actually already known before. It was not really formulated as this, but Eliashberg and Polterovich showed that the geodesic distance of the H-1 metric on the symplectomorphism group, which is kind of related to Hofer's, it's Hofer's LP metric. So there's the Hofer metric, which is the L infinity version, which is fine, but the LP version has a degenerate geodesic distance function, and this was proven in the 90s by Eliashberg Polterovich. I don't want to give you a full proof of this result, but I want to show you what the computer showed, Peter and David. Namely, it showed that if you, this is kind of an example here, we try to minimize the energy from the line on the bottom to the line on the top. And what happens is these kind of zigzag curves come out until they reach the top and then they get retracted. And as you add more and more points to the discretization of your curves, you will get more and more teeths. And this indeed will make the energy shorter and shorter. Maybe not super clear, so let's try to do something else. Let's try to do an easier example. Let's try to do an easier example where I can really explicitly convince you on one slide, hopefully convince you on one slide, that there exists Riemannian metrics with vanishing geodesic distance. So we consider an even simpler infinite dimensional Riemannian manifold, namely the space of L2 sequences, and we equip it with a certain Riemannian metric. And it's kind of nice because this example really mirrors the behavior that we also see in the L2 metric on the space of curves. It's just separating it a little bit and makes everything easier. So what do? So we take the L2 inner product, but we weight it by an additional sequence mi, and we also weight it, we add a conformal factor in front of this, which is just f of the foot point, of the L2 norm of the foot point. Okay. And I claim that the induced geodesic distance then vanishes. So I should say this example is an adaptation of an example that has been found by some Italian mathematicians a couple of years ago, 2020. Okay, so how do we prove this? We take two arbitrary L2 sequences, and it's kind of based on two observations. The one observation is we have this weighting factor by the foot point here, f of the L2 norm of x squared, and we take some function that goes to 0 for y towards infinity. So if we sit at the point, if my x, my foot point, has a very large L2 norm, I can do whatever I want because I just multiply it with something that goes to 0. So that's the first ingredient. What is the second ingredient? The second ingredient is that I weight my L2 inner product with the sequence mi, and the sequence mi goes towards 0. So in some way, it does not punish high frequencies. So if I go very far out in my L2 sequence and only change something in very late entries, this is also free. Okay, these are the two ingredients. So what I do is, I have x and y, and what I do is, I first start with x, and I change very high frequencies. So I add something that is only living in very high frequencies. So En is just the standard basis. So E1 is 1, and then just zeros. E2 is 0, 1, and then just zeros. And I just add to my point very high frequencies. And if you look at this, and if you calculate the derivative, you see the derivative is just En. And if you plug this in, my foot point doesn't do anything bad here. There's just, let's ignore this part. But if you just calculate the L2 inner product of this, you see that this becomes small. Okay, that's the first good thing. So we can go out here. What do I do then? You realize at the end point of C1, Now you are at the point that has a very large L2 energy. So now the F term multiplies everything down, and I can do whatever I want there. And so what I do is, I'm staying at my point that is disturbed by these very high frequencies, and then I just go linearly to my target, kind of to my target. I'm not yet at my target, but I'm at my target plus some very high frequency. And then I just go back to my target, and this has again small energy by the same argument as it had small energy to disturb my original point. In many ways, this is a toy example of what we have seen before, because if you think about Fourier space for curves, that's exactly what we did. We kind of disturbed it. This is just very high Fourier frequencies, and then we went straight up. So it is really, it's very simplified because we really separate these two contributions, and in the metric on the curves, on the invariants, everything is kind of combined, and we have to work much harder with smoothness and to make sure that all the estimates work. But in the idea, this is the proof in a nutshell. And for all of the cases that we know, kind of a similar proof actually works. Okay, so the L2 distance says all shapes are the same, so it's not a good idea to use shape analysis with this, because if it says everything is the same, it won't lead to any interesting properties. But we know there's L2 spaces, and if L2 spaces are not good enough, what do we usually do? We probably look into Sobolev spaces. And we can do the same thing in an invariant way. So instead of just integrating the L2 norm of the tangent vector, we want to integrate some Sobolev norm of the tangent vector. So we include the Laplacian, and since we want to have everything invariant, we use the surface Laplacian, and then it's an easy exercise to show that this is again an invariant Riemannian metric. One thing that is important to note here, this Laplacian really depends in many ways on the foot point. And so you have to take this into account when you calculate your geodesic equation, or also when you discretize the Riemannian metric. Just for the simplest example, curves, I have written down how the Laplacian depends on the curve. For surfaces, of course, it gets a bit more complicated. And if you choose p is equal to 0, then you regain the L2 metric that we have studied before. So the first question is, does this help us? Does it at least overcome the degeneracy that we had before? And the answer is yes, it does, which is good. So what do you need? Essentially, you need order 1. If you have a Sobolev metric of order 1, you are good. In dimension 1, greater than order 1/2 is enough. Yeah, that's it. So in dimension 1, you need more than order 1/2, and in dimension 2 or more, order 1 is already okay. The proof of this is really differing in which situation you are. You will need some different types. One thing that is kind of nice, if your metric is really high, if the order is really high, then you can indeed interpret this as a strong Riemannian metric on some Sobolev completion, and then you get a lot of things for free, including you get for free that the geodesic distance is possible. In dimension 1, the proof is just based on the Sobolev embedding theorem, and you need order 1/2 for this. The proof for order 1 is slightly more geometric and slightly more tricky, but it's still pretty straightforward. But if you, there is, on the other hand, that is what I should say. On the other hand, it's not clear what happens below this. So we don't really know if these are strict estimates. So we don't know if they are necessary. I would believe they are. Why? Because if you restrict yourself to the diffeomorphism group, it has been shown that they are indeed strict, which has been done by a little bit by myself, but also a lot by Sima Orr and Bob Gerard from the University of Toronto. And they have this very nice paper where they showed, where they disproved something that Peter, me, and Philip conjectured. Namely, they proved, because we thought it would be the same in any dimension, and they actually showed that in higher dimension, the vanishing goes further and further. So not further and further, but in dimension 1, it vanishes up to 1/2. We knew this already. But as soon as the dimension of your domain is more than 1, it's vanishing up to order 1. And it's a very sophisticated and very nice construction. So This is still open in the context of emergence. I would believe that vanishing up to order 1/2 is quite doable. Actually, we tried this with C and me tried this with a postdoc of us, with Patrick Heslin, and we did some progress, but there was essentially only technicalities that prevented us, but it was a bit technically tricky, and so we didn't get all the way there, but it should be possible. The case 1/2 to 1 is very difficult. I would think in the context of emergence, I would not know how to do it, and I would not even want to tackle it, because the construction on the diffeomorphism group is extremely subtle and extremely complicated, and I would not want to touch it. But I believe it's true. Okay. I want to spend just a little bit of time to talk, very little bit of time, to talk about a conjecture that is also due to Peter and David, and which kind of bugs me since a long time, and I never really managed to prove anything, but I would still hope that there is a chance that we can make progress. So the idea is, what are the reasons of vanishing geodesic distance? What is happening in vanishing geodesic distance? In some way, how we should imagine this is we should imagine the shape space or curves as a very, very hilly landscape. And in fact, if I want to reach a point, there's always a larger hill which I can pass around. In other words, there's a lot of curvature. And so for all the examples where we know that there exists vanishing geodesic distance and where we were able to calculate the curvature, because this is non-trivial in infinite dimensions, we observed that the curvature is actually positively unbounded. I don't think that this is an equivalence, so there is examples of spaces with positive unbounded curvature that have not vanishing geodesic distance, but I believe that the other implication might be true, so that as soon as your curvature is bounded, I believe that the geodesic distance should be well behaved. But I don't have an idea how to tackle it, and it seems pretty difficult. But I would be happy if anyone wants to work it. In fact, with Steve Preston and with Alice, we are trying to kind of do this, like a full characterization of this on the diffeomorphism group to hopefully get more evidence and maybe see some of the mechanism behind it. But it seems challenging to prove this in the context of general infinite dimensional manifolds. Okay, so we have now a Riemannian metric with a well-defined geodesic distance function. Now we want to calculate geodesics. The first thing we do is we calculate the geodesic equation. And as already mentioned, these are related to many famous equations in geometric hydrodynamics. And here is a list of some of them. This is in no way a complete list. I think I really like the article by Cornelia Wiesmann. She has an article where she gives an overview of a lot of different equations that can be found in this way. But the article is already about 10 years ago, and since then some new examples have been found. Probably the most complete list that I know of is in the new version of Boris Haitian's book. But even since then, which is just 2 or 3 years ago, several new examples have been found. So this is really kind of an ever-growing list, but it should just show you that this is really not like a singular phenomenon, but this is kind of really a broadly applicable approach to many PDEs. I think one thing that is worth to mention here is I said the geodesic equation doesn't exist. What does it mean that the geodesic equation doesn't exist? I write down a Riemannian metric, I do calculus of variation, I get something. This should be the geodesic equation. If you think what the geodesic equation is given, it is given by this formula in the second line here. I can write this formula always down because the right-hand side is well defined. But if you look a little bit careful here is, you see that you have G of gamma of the Christoffel symbol essentially. And this is not, the Riemannian metric is not invertible. And this is exactly the source why the geodesic, in this sense, the geodesic equation might not exist. So I can always express the second line, but I can maybe not extract an explicit formula for gamma if G is not a strong Riemannian metric. In other words, you have to show that the right-hand side takes values in a smooth dual, which is the image of the tangent bundle under the Riemannian metric if you want to show that the geodesic equation exists. What would be a simple example of a geodesic equation that does not exist? In fact, take the Riemannian metric that I showed you on little L2. If you calculate it, it's a 2-line calculation to show that this will have no geodesic equation in the sense that you cannot explicitly express it just because it will not make sense. Okay. So you already saw all of these famous PDEs, so it seems it's really a non-trivial question if the geodesic equation is A, locally well-posed even, but even more globally well-posed. I will talk a little bit about local well-posedness, but not very much. I think local well-posedness is mostly solved. I believe the results are essentially sharp, although we have not shown that, but I don't think that you can go much lower in a Sobolev regularity. It's different on diffeomorphisms on emergence. On emergence, you need order 1. On diffeomorphisms, you need only order 1/2 of the metric. But as long as you have this, everything is fine. We don't want to go below 1/2, and I think we also don't want to go to below 1. So I don't really care how sharp these results are. There is some work for the L2 metric that is by Konstantin Kapala-Topolov, where they really showed, at least in the L2 case, the geodesic equation is really ill-posed in the sense that the exponential map is not even C1. This has not been generalized to other values, to positive Sobolev metrics. I think it is doable. It's probably more technical, but I think it's doable, but maybe not the most important thing here. But I think the proof is very nice, so I want to say some words about the proof. 3 words about the proof. So the idea is the same, to do the exact same thing that what Eben Marston did for the Euler equation. And it's kind of nice. So what you do is, the problem is, we are on a Fréchet manifold here per se, and on a Fréchet manifold, we don't have a theorem of Picard-Lindelöf. So we cannot even solve ordinary differential equations. But if we consider it not on smooth curves or smooth surfaces, but instead on Sobolev curves and Sobolev surfaces, we are suddenly on a Banach manifold. On the Banach manifold, we can use Picard-Lindelöf. So why does Picard-Lindelöf help me? Because you say this is kind of a PDE, why should this help me? The answer is, in this Banach completion, one can show that many of the Riemannian metrics that we have here can be interpreted, where the geodesic equation can be interpreted as an ODE on this Banach space, because the whole right-hand side in the geodesic equation is a smooth vector field. And now we can use Picard-Lindelöf. Okay, there's a lot of it hidden here, but that is kind of the essential idea. You extend the metric to a space of rougher elements. There you can interpret the geodesic equation as an ordinary differential equation. Then you use your nice Picard-Lindelöf or Cauchy theorem. You get local well-posedness in a Banach setting. Are you done now? Not completely, because you don't want to do it. You want to show smoothness for smooth initial conditions. I mean, this is what we often want for PDEs. So why does this work then? Because there is what is called the Eben-Marston theorem, or the no-loss, no-gain theorem, which also applies to this setting, which tells you if you solve certain PDEs that have a certain invariance property, then the solution stays as smooth as the initial condition. And so now you can apply this, and you can use this to transport your result back from the Banach category to the Fréchet smooth category. Okay. A 2-second version of this. In some way, local well-posedness is nice. It's a very interesting property if you are interested in analysis of PDEs. But if you're interested in shape analysis, local well-posedness is actually not what you're really interested in, but what you really want is completeness. Because completeness tells you can compare any 2 objects. Several different completeness properties, we will talk about this. But it essentially tells you Cauchy sequences are well-behaved. It tells you the matching problem will be well-behaved. So completeness is what we would, in an ideal world, always want to have. And unfortunately, it turns out here much less is known. For curves, it has been resolved, and it's even sharp. So for curves, it has been solved. If the order of the metric is larger than 3/2, you are good. This has been done by Peter, Martins, and David for order 2, and has been later extended to greater than order 3/2. But it says as soon as your metric is kind of strong enough, everything is known. On diffeomorphism groups, it's also resolved. It's not known that on diffeomorphism groups it's sharp, but pretty much believe it. And here you need just the same thing as for curves. You need to be above the Sobolev threshold, +1. So you need to be above dimension of your domain, +1. For surfaces, unfortunately, nothing is known. We don't have any example where the space is either metrically or geodesically complete. I believe the same as on the diffeomorphism group is true. And I'm trying to prove this since roughly 10 years. And every couple of years, I think I have a new idea, and usually it doesn't work out. But I will come back to this in 2 minutes. So what is the problem for completeness? Why is completeness so tough in infinite dimensions? In finite dimensions, we have the nice theorem of Hopf-Rinow that probably most of you know, which says there's 3 different completeness properties on a manifold. There's geodesic completeness, which means the geodesic initial value problem is globally well-posed. So if you take any initial values, your geodesic will exist for all time. Then there's metric completeness, which says that the manifold is a complete space with respect to the induced geodesic distance. And then the third is the existence of minimizers, which says any 2 points can be connected by an minimizing geodesic. So the theorem of Hopf-Rinow says metric completeness is equivalent to geodesic completeness, and both of them imply geodesic convexity or existence of minimizing geodesics. What happens in infinite dimensions? Essentially nothing is true. For strong Riemannian metrics, you can show that metric completeness still implies geodesic completeness, but this is all. And for every other of these properties, there have been actually constructed counterexamples. This is done by most of this work is done by Etkin. He actually wrote a paper that is called the Hopf-Rinow theorem is wrong, but also by someone with connections to the Erwin Schrödinger Institute. So also Ivar Ekkeland should be mentioned here, who got the Schrödinger medal a couple of years ago, who did a very nice follow-up paper to Etkin's paper to showing some of the other converses. I just want to give you an idea of the proof here. And I believe I will stay more in the theory part of my talk as I planned. But I want to give you just an idea of the proof. The proof is again, the counterexample can be again constructed on little L2. And it's called Grossmann's ellipsoid. And essentially you build an infinitely long ellipsoid where you can show that you have no geodesics, although it's complete, you have no geodesics from the North Pole to the South Pole. Okay. Geodesic completeness does not imply metric completeness. Actually, Etkin wrote, I kind of like this quote because I think he is in some way wrong here, because he said it's very difficult to envision any natural example that is geodesically complete but not metrically complete. And then in the 90s, he constructed a very complicated example for this. But I would argue there's a lot of natural ones, namely all of the ones that we have in our area. If you take any Riemannian metric that is complete on the smooth diffeomorphism group, it will never be metrically complete. Similar for emergence and curves. But I'm cheating here a little bit because Etkin probably was only talking in the context of strong Riemannian metrics. So this is really not what is the case here. But still, I think there's a lot of natural examples that are in fact geodesically complete, but not metrically complete. I like the proof of metric completeness and completeness. So I again want to just spend like 2 of my remaining 10 minutes for this. So how do we prove well-posedness, global well-posedness? The idea is, for all of these metrics where we know that the geodesic equation is globally existent, we could observe that you can always extend it to some Banach or Sobolev completion where it is in fact a strong Riemannian metric. So that's what we do. Instead of looking at them, similar as in the local well-posedness proof, we will not look onto smooth category, but we will go first to the Sobolev category where it is a strong Riemannian metric. But then we are not done yet. Then we have to work very hard to show that on metric balls, certain quantities can be controlled. And this allows us then, so we show 2 things actually. We show that on metric balls, we can control the immersion property. And then we show that on metric balls, we can compare our invariant metric to some flat background metric. And this control is the constants that you have here are controlled on metric balls. So they don't depend on your geometry anymore. Once you have this, you are done, because once you have this, you get metric completeness. since you have a strong Riemannian metric, the metric completeness, you have the one theorem of Hopf, the one statement of the theorem of Hopf-Greenhoff that still is true, you get geodesic completeness, and then you use again the Ebin-Marsden trick and get geodesic completeness in a smooth category. Okay, so what goes wrong? What goes wrong for surfaces? 3 and 4 go wrong for surfaces. All the other steps work also for emergence in general dimension, but 3 and 4 go wrong for surfaces. So you might ask now, but why does it work for diffeomorphisms then in higher dimension? Because 3 and 4 seem also difficult for diffeomorphism groups in higher dimension. The answer is diffeomorphism groups, it's kind of magical, everything comes for free. Once you see that it's a strong Riemannian metric, you are done, because you have a strong right invariant metric and then completeness follows by general arguments. So diffeomorphism groups is nice that it's true, and it's an indication that it might be true, but it's kind of magical that it works out and it works out for free. So you don't have to do the hard work in 3 and 4. And since it's kind of the problem that I'm thinking the most about right now, I want to say one slide about this as well. So what is the main ingredient? The main ingredient that we need is, and one of the reasons that I want to spend 2 minutes is that yesterday after a talk, I got finally some help, and I want to thank you for this. And it's kind of maybe, if this works out, this 5 minutes conversation paid out for my flight. So I was really stuck with this, but I was yesterday pointed towards a certain class of Sobolev inequalities that we didn't find for years, so it's great. But yeah, so let me say. So what we need to do is we would like to have an L infinity estimate. So this is kind of the main ingredient in the proof. So we would like to have an L infinity HS estimate, but the problem is that we need a very exact control of the constant and how the constant depends on the foot point, on the surface, or if you want, on the surface metric. So how is this for curves? For curves, it's trivial, because curves essentially, we are on a one-dimensional manifold. One-dimensional manifolds have no geometry, there's no curvature. So we can just take one derivative and mimic the standard proof of the Sobolev embedding, and we get that the constant depends on the total volume, or the total length of the curve. Unfortunately, this does not work out, and this is really, once you have this, I mean, it's hard estimates to get the completeness, but this is kind of the main ingredient, I would say, that is missing for surfaces. Yeah, and I was looking quite a bit in the literature, but apparently was looking wrongly. And there is some, in the theory of Willmore floors, this is apparently used. It's not exactly giving me what I need, but I think there is some hope to find some equivalent using something which is called Michael-Simon-Sobolev inequalities. So what we would need is, of course, we cannot hope to have H1 here, but we would have hoped to have H2 here. And of course, we will not only get a constant that depends on the total volume, but there will be also some curvature terms involved here. And that's exactly what it seems from these estimates that I got shown that happens. But now we need to control the quantities. In particular, we will need to control mean curvature on metric balls. But this seems possible as it's kind of the right orders that appear in the metric. So I'm very excited about this. That's fine. 5 minutes. No, I'm in time. So instead of showing you talking about the numerical discretization, I will say there will be a talk about numerics next week by Emmanuel, where you hopefully will see some of the things. Actually, it will be a little bit different, but you will still see some of the things. But instead about talking of this, I just want to show you some examples. So this is not only a theoretical framework, but we really implement this. This is open source available. In fact, H2 type metrics we did H2 type metrics on surfaces. If you think about the results that you saw before, you might now say or complain that H2 is below the completeness threshold. It's exactly the critical index. I think for numerical purposes, it should be enough. So if we took H1, we took H1 first, and we really saw singularities happening. We saw really kind of bad things that happened that kind of suggested that first order metrics were not strong enough, at least not for how we implemented it and how we wanted to do it. And we really saw the properties of the theory kind of visualized in the numerics. But for second order metrics, which is exactly on the critical threshold, it seems to behave well. And if you think about the all of this is based on Sobolev embedding theorems. And if you think about the counter examples at the critical thresholds, these are really like very, let's say, exotic, but very singular functions that you might not see in a real data situation. So the first thing that we see here is I just want to mention, like, the framework is capable of dealing with relatively complicated surfaces. We have, I mean, this is a rather simple example, but we have implemented a multi-resolution framework. What do I mean with this? Given if you have two surfaces, there's a lot of local minima in this space because we have a lot of curvature. So what can help is, instead of solving your matching problem immediately on the highest discretization, you can first downsample your surfaces, solve on a lower dimensional discretization, and subsequently upsample the solution. This is what we see here. Maybe one thing that I want to say here, I kind of promised to connect this to Blanche's talk, and I was really slow today, but I want to say they're kind of the maybe most difficult things in like really implementing these metrics is how do you deal with the reparametrization action? And there's several different approaches towards this. And what we did is we did not explicitly implement the reparametrization action because we wanted to have something that works in the context of real data. So we did the same thing what Alain would do, or what Alain and Lara did. Instead, we consider a relaxed problem where we solve it and we just have a similarity term that is blind to reparametrization. And what have we learned this week would be the best term to use this, that is completely not seeing the reparametrization, the variable distance. And that's exactly what we did here. So we took our Riemannian metric, but we relaxed the boundary constraints using a variable distance. And this allowed us to bypass the explicit discretization of the diffeomorphism group. And without much statement, you just see here some geodesics in the space of surfaces. And I mean, I don't think that there is too much that I want to explain about this, but it just says we can deal with significantly large deformations and also with different topologies of the data. So we do not require that we have an S2-shaped surface, but as you can see, for example, with this data, with the skull-shaped tape on the right, we can have kind of arbitrary topologies, and the pipeline still works. We have also implemented methods like motion transfer. So what you see here is we took a motion. So you see the motion on the very left, and we transformed the motion from the violet to the two shapes on the right. Maybe one other example where we transfer the motion from the cat to the motion of the mountain lion. And it's kind of interesting to see, but I mean, there exists, which might be coming partially to a mismatch, but if you look carefully here, you might see a tiny singularity that is happening there, which, I mean, might be either because we have not found perfect point correspondences or for some other reasons. And this is one final last example for motion transfer, where we transfer motion from the violet to the turquoise shapes. These are all fairly low parameterized examples. There is some, I mean, there's computational cost certainly involved with it. It depends. If you have millions of vertices, I think we cannot handle it, is the answer. But we can do fairly complicated surfaces, and I think it is somewhat fairly stable. I mean, there is a question about parameter tuning when you want to use it, but it works in the context of real data. And in fact, what Emmanuel will show next week is how some of these methods can be replaced by kind of deep learning based methods. And I think there's kind of a lot of benefit that we can get out of this. But all of it is open source available, and I would be happy if people want to work with it. And here I should also, of course, thank to Shaw Fady, because without PyChaos, all of this would not be possible. Yeah, with this, I'm perfectly in time, and I stop here.